Welcome everyone to this rock physics analysis using the Wavelet software session. I would just give you a quick brief about this session. Basically, we would not be doing much more advanced things, but the basic concepts of rock physics and how to use them using a quick educational software. But before we start using the software, we would go through some of the very foundations of rock physics, because we have seen that most of you have been using these techniques, uh, but the problem is that you may not be having a clear understanding of these things. Like you must be doing Facies modeling, but what is the concept behind this? So we would be trying to have a clear concept of all these things. So this would be our agenda. We would take a quick review of the rock physics. Then we would discuss, this is my way of defining the things, that we would see what are the red, green, blues of rock physics. Then we would go into more details, such as using regression or statistical techniques for creating empirical relations between various parameters. And then we would go through rock physics templates using various cross plots. And then another thing, attribute space. This is something I have defined the cross plots into a new manner. So we will discuss what is this attribute space. It is the same cross plots, but we can increase the dimensions. And finally, we would have 3 sessions related to Wavelet software, basic introduction, followed by Wavelet software using regression analysis and multi-regressions. And after that, we would be using Facies modeling and all those clustering techniques. We start with the rock physics. By definition, rock physics is an integration science which links the seismic, petrophysical logs as well as the core data and establishes empirical relations between various rock properties. We know that petrophysics is basically physics of rock. The term petrophysics is generally used for the logs or physical properties that have been measured by the wireline logs, whereas rock physics, we would refer more to establishing correlations between various other parameters. Rock physics also plays an important role in quantitative interpretation, because in quantitative interpretation, our major aim is to convert the seismic response into rock properties. So like we know, in inversion, we compute the acoustic impedance, and then from acoustic impedance, we can compute backward all other rock properties. So rock physics always plays an important role. And once we have, through inversion, we have computed certain properties, then using various regression equations, we can move backward and compute all those other parameters. We would see that there are no set of rules in rock physics. Relations that hold true for one area may not be valid for another. Or if you find correlations between 2 rock parameters in one area, the same correlations would not be valid in another area. So first of all, we have to explore the correlations between various parameters, which may be petrophysical logs, computed elastic logs, and as well as seismic derived attributes. All advanced quantitative seismic interpretation techniques such as inversion, amplitude versus offset, everything is based on rock physics model. Okay, we look at a very simple inversion and forward modeling concept. We know that rock is composed of 3 things. It has a lithology, it has porosity, and within the porosity, it has certain fluids. So now through computer modeling, we can also do the same thing, that using these 3 parameters, we can do fluid and lithology substitutions, and we can compute the elastic properties. And once we have the elastic properties, from these we can compute the velocities and densities. And then we can have the acoustic impedance reflectivity series, and we convolve it with a wavelet, and we get the seismic response. This we can do as forward modeling on the computer, but in the real earth, the same thing is happening, that the seismic response that we get is basically due to the rock's basic constituents, that is the lithology, porosity, and fluid. And these three things govern the elastic properties, which in turn control the velocity and density. And because of the contrast in these parameters, we get the seismic response. And similarly, in inversion, we are moving backward. We compute the acoustic impedance, and somehow we break the acoustic impedance, which is the product of velocity and density. And then using further inversion or correlations, we can compute the elastic parameters. And further, we can interpret them into lithology, porosity, and fluids. So this is the same thing which I discussed, that we have lithology substitution, porosity, and fluid substitution, which generates the elastic parameters, which in turn generate the acoustic impedance, which is the product of velocity and density. And so we are getting the seismic response. One thing which I have termed as red, green, and blue of rock physics. This is the concept from the color theory, that we know that if we have red, green, blue colors like in our computers, so by mixing all these three colors, we can virtually generate all those millions of colors. So here, what we say, that the rock's physics story begins with these three red, greens, and blue, where red is the compressional p-wave velocity, the green is the shear wave velocity, while the blue is the density. What we mean is that if we have these three properties measured for a rock unit, we can calculate all the elastic moduli, and then we can correlate them with the petrophysical parameters as well as seismic attributes. And then we can create correlations between all these parameters. So here we can see in these all set of equations that we start with if we have just the p-wave velocity, from that we can compute the shear velocity as well as density using the Castagna and Gardner's equations, and then all these elastic parameters can be computed. So basically what we have seen, basic parameter of seismic is velocity. And all the information of the rock, like elastic parameters, geometric and fluid parameters, are encoded within the velocity. So velocity is the net resultant response due to which we are getting the seismic impedance. So similar to the white light, which is a composite light and which is a mixture of rainbow colors, and through the prism we can split them into those rainbow colors. So similarly, we can split the velocity into its constituent components. So if this is the velocity, we can break it up into a range of elastic parameters. So what is the need of breaking and splitting the velocity into these elastic parameters? So for that, I would just give a simple example of student scores. Let's suppose we have three students, A, B, C, and you can see their scores. From this total score, you can see the student A has the highest marks. And suppose we have to select a student for engineering. So it means we would say student A is the best student because he has the highest marks. But if we split the total score into various subjects like this, so then we can see student A had good marks in various other subjects like English literature, history, and geography, whereas in most of the science subjects and engineering related things like physics and mathematics, his score are lower as compared to student B. So when we see the detailed mark sheet, so our choice for the engineering student would be student B rather than student A. And similarly, if we can say, if we are considering a medical student, so then our choice would be student C because he or she has good marks in biology and chemistry. So similar to this example, when we have the composite velocity information, it is the net resultant of the rock's response in terms of seismic. So it means we cannot encode most of the other properties. So it means when we break the velocity into various elastic parameters, it has a different response to various rock properties. So that's why splitting these velocity into other properties is useful in interpreting the response of various properties of the rock. So that's why we need to split velocity into its constituent components. There are certain limitations with this technique. The limitation is that mostly if we have just the p wave velocity, and from that we are computing the shear velocity and then density, so it means all alone from that we are computing everything. So that's why the focus is that originally the best results that we would be getting is that we should separately measure in the field or in petrophysical logs the p wave velocity, shear wave velocity, and density. While if we are computing the shear component or the density from the velocity, so there would be certain limitations for that. And that is clear. You can see from here. Here you can see the p wave velocities for different rock units. So let's suppose we have this sandstone sample and it has this velocity. And then we have a coal, it has the same velocity, and we have a shale unit which has the same velocity. So it may happen like that because their velocities are overlapping. But in nature, this would never happen. S wave velocities would be different. So the red was their P wave velocities, which were the same, but if we measure their shear velocities, they would be different. So it means in this way, we would be able to differentiate between them. But if we are using, let's suppose, the same p wave velocity and using any regression equation, if we have converted and computed the shear velocities and we have not measured them, so we would get the same results, though no matter it is sandstone, shale, or coal. So the problem with computing and not measuring the shear component, that in all the three cases, if we have the sandstone, shale, or coal, and all three have the same velocities, and when we would compute the shear velocity, we would get the same result for all the three samples. Whereas in reality, when we are measuring the shear velocities, they would be different. So that's why it is better to have a shear component computed from the p wave velocity, because something is better than nothing. But the good thing is that we should always try to measure it. So here we can see cross plot of two things, the VP velocity and density. So in the top example, what has happened that P wave and S wave both have been measured. So you can see the scattering of the data. So it means like in Facies modeling, we would be able to classify it. Whereas in the second case, the S wave has been computed from the P wave through a linear regression, and now the cross plot between bulk modulus and VP is also a linear straight line. So it means we would not be able to classify things based on this thing. So here we have just some examples, like once suppose we have the velocity, so we can split it into various rock properties, bulk modulus, shear modulus, and all these things. Similarly, like if we have seismic stacking velocities, RMS velocities, we can convert them into interval velocities, and then we can convert it into density, bulk modulus, Poisson's ratio, and all those elastic moduli. So we would call this as a 2D velocity inversion, because from the velocity we are moving backwards to other rock properties. We can do the same if we have an interpreted horizon, and then along that we have picked the velocities. So we have the velocity contour maps, and then using those relations, we can compute bulk modulus, Poisson ratio, and all these parameters. Okay, another thing that is a very commonly used in rock physics is regression analysis. Regression means simply computing empirical relations between two rock properties. So suppose we have taken a lot of samples in an area, and for all those samples we have suppose measured the p wave velocity and densities, and then we can run a statistical least square regression between them. And if the correlation is good, so it means that equation would be valid. So before going and discussing this, I would just put a simple equation. This is Newton's second law, F is equal to ma. So this is basically a deterministic equation. So before discussing this empirical relations, we should have an understanding of what is the difference between deterministic and probabilistic. So like this equation, F is equal to ma, this is a deterministic equation. So it means anywhere in the universe, this equation holds true. That is, the product of mass and acceleration would always be the force, and we compute it here on Earth or on Mars or Moon or anywhere in the universe, this equation would give the exact same results. So now, where comes the empirical relations? If I add certain error e to this equation, so it means I am introducing some uncertainty into it. So there, it means when I would be computing the value of f, so because of the error, I would have some plus minus error or uncertainty into my results. So there would be a probability of different results within the standard deviation of the error. So it means in this case, I will not be having an exact equation, and it would be a probabilistic equation because I would not be having an exact result. So here these regression equations would be coming. So it means all these equations are not exact equations. They are giving you results within certain probability range of the errors, which is usually referred as the standard deviation. So here we try to understand the regression. This is, if you consider this first part, that is a naught plus a1 into x. So this is the equation of a straight line, where this is the intercept and this is the slope. And this would be the linear first order regression. That is, it would fit a straight line between two parameters. And if we add the second order, so it means this would be a quadratic second order regression, and a2 is term added to it. And that would be basically the curvature, and so on. We can add the third order, and so on. We can compute other parameters. So here we can see we have two parameters, 1 and 2, and they have been cross plotted. And if we have the first order equation pass through it, so it means this would be the equation, and you can see this is, it has a slope, it has an intercept, and this would be the equation. So in a similar way, Castagna derived his equation. He took a lot of samples for siliclastic rocks, and he computed the p-wave velocities and shear wave velocities, cross-plotted them, and computed a regression equation. And so that was this equation. So practically nowadays, we don't use this equation because this is just a starting benchmark. So for our own area, we would try to have, if we have sufficient data, so we would be computing our own equation between p-wave velocity and s-wave velocity, because it would be more representative of our local area. Okay, similarly, if we have in our data different rock units as shown by the colors, so it means again, it is not valid that we should pass the same equation between all these data sets. So it means if we pass a higher order curve, so that would be better because the slope is gradually changing. Or if we, what we can do is we can split the data and we can have a slope between all these parameters, and each slope represents a different rock unit. So in this case, we would be having a multi-regression, that is for different rock units, we would passing a different regression line for each of the different rock units. So that would give us more realistic results. So these are certain examples, real examples, and these have been generated from the Wavelet software. So here we can see a first order regression between VP and VS. This is the same data, and you can see now a second order regression has been passed, and here it's multi-regression. That is, you can see different colors and you can see dotted lines as well. So you can see here for this interval, this was one rock unit. So it means this had a different regression equation passed through it. In this case, this rock unit was different, so a different regression equation was passed, and so on. We have split the data into 4 different rock units, and here we have 4 different equations. Whereas in these two, in this case, for all the different rock types, we have just passed the same regression line between all the rock units. So naturally, as we talked about uncertainty, so it would be giving us results, but this would not closely approximate the real nature. Whereas here, since we have broken the data into different rock units, we are using different equations, so that would give us a better representation of the reality. As I talked about, the correlations that exist for one area may not be true for another area. So here you can see we have different properties, like this is p-wave velocity, shear velocity, density, this is resistivity logs, gamma ray, porosity, bulk modulus, and so on. So what we are doing, the software is computing correlations between them, and then it is marking them. Like red one is those which have a correlation coefficient of above 80%. Then the orange ones are those which have a correlation coefficient above 0.6 or 60%. And then the blues and blacks ones have lower correlation coefficients. So just computing these parameters, and the software just gives us a correlation analysis that in this specific well or a group of wells in that area, this is the correlations, that certain parameters are well correlated while other parameters are not so well correlated. But if we try the same thing for another area, we would see these correlations may change. So it means the response of rock properties from area to area changes. So this is very important. So before doing any rock physics analysis or computing the empirical relations, we have to see which two parameters more closely match each other. So it means all those red ones would be the ideal things between which we can derive the empirical relations, whereas our second choice would be all those orange or amber colors, and then blue ones and black ones, they would not be good. They cannot be used because the correlation would have a large amount of standard deviation error in them. So usually this is the workflow that we usually adopt for the petrophysical logs. We have the data, we select the range of data. Suppose there are glitches in it or bad things, some errors in that. So first of all, we have to filter the data. And then if there are multiple wells, we have to integrate the data of all those wells. And then we do this correlation analysis that I showed you, and we identify what are the parameters which have good correlations. And then we use the data for those parameters and run regression analysis to compute empirical relations between all those parameters. So here, this is one example. Like here we have, in this green one, here we have a lot of glitches in it. And here you can see in the histogram, we have this glitched values. And here in the cross plot, you can also see all these zero values. So all this is because of glitches or bad values in the data. So it means naturally when we have to run the regression, we have to filter all these data components. So here you can see the three views of the data. This is the log versus the depth. Here it is the histogram, that is the distribution of values, which indicates that these values occurs more highly in the data. And whereas this is clearly showing us that this is the error. And in the cross plot, these are the bad points. So now we apply the deglitch filter. So you can see all these values are removed and all these bad points have been clustered here. And now the histogram is also fine like this. So first of all, we have to do the data refinement and filter all the bad points before running anything. And now we have the P wave and the shear wave, and you can see we can run a correlation between them. And again, the more data we have, the more real representative of nature it would be. Here we can see another correlation between resistivity, log, and P wave velocity. Here these dotted lines basically indicate the standard deviation, that is most of the data, if it lies within that, so it means the correlation is good. This is another example of porosity versus velocity. This is also fine, but as compared to the previous example, we can see that the data is more scattered, but still it has a relatively fine correlation. Now this is gamma ray versus velocity. Here you can see the data is more scattered, so naturally the correlation would be lower. So we have to think if it is acceptable or not. But if it is above, let's suppose 60% correlation, so we can still consider it. Here we can see, using these regression equations, the red one is the shear velocity that we have measured. The blue one is the shear velocity computed from the P wave velocity using the standard Castagna equation. The green one is the shear velocity computed from the regression equation that we have derived locally from our area. So as we can see that the green curve closely matches the red one. So it means when we are deriving our own empirical relations for our specific area, they would give us much more better results as compared to the standard Castagna equation, because that is not the real representative of our area. It means we have to compute all these regressions. And from this, you can see regressions are very important in rock physics, because our aim is to establish relations between various parameters and then convert one parameter into the other parameter. The next thing was rock physics templates. We have the petrophysical logs. Let's suppose we have a gamma ray. I'm talking about simple petrophysical log interpretation. So just from the gamma ray log, we can differentiate from the reservoir and non-reservoir rock. Now, if I have the porosity log, I would be able to compute the porosity. So within the reservoir, if the porosity, let's suppose, is greater than 10%, then it is a good sand. And if it is below 10%, I would say it is a tight sand. Now the interpretation has changed. And finally, like if we have the resistivity log, so we can compute water saturation, and from that we can have an idea what are the various concentrations of the fluids. So it means from this example, what I mean to say is that a single log would just give us one simple interpretation. Having a combination of different petrophysical parameters, we can have more better interpretations. So in a similar fashion, when we split the velocity into various elastic parameters, so by combining the interpretation of all these individual parameters, we get a more realistic result. One of the most common way of interpreting data is using cross plots. First of all, we can see that these logs on the left side are like this is acoustic impedance, this is VP/Vs ratio, and this is gamma ray, and all these logs are plotted as a function of depth. Whereas on the other side, we have the cross plot, where two physical quantities are plotted versus each other. I call this cross plot as attribute space, which we would later see it has certain new meanings. If I consider the cross plots, on the left side we have the depth domain, where everything is plotted as a function of depth. So if I take VP/Vs ratio or even acoustic impedance, both have been plotted as a function of depth. We know that in physics, most of the physical quantities are function of time or space. So these are the basic dimensions. So here again, it is a 1D data, and these two logs are plotted. Once we have this depth domain, it means what is happening that if on the other side, this is the attribute space. So what in the attribute space we are doing, that instead of plotting any physical quantity as a function of space or time, we are plotting one property as a function of another property. So all these properties are basically attributes. So that's why I call this as an attribute space, because here we would be plotting one property as a function of the other. So if I take VP/Vs ratio, so in this depth domain, VP/Vs is plotted as a function of depth, whereas in this cross plot, VP/Vs is plotted as a function of acoustic impedance, which is basically another property or an attribute. So that's why I call it as an attribute space. Now if you consider this, and I've just plotted a line at this depth interval, and let's suppose I take two values. So here the acoustic impedance value is 12.9, whereas the VP/Vs ratio value is 1.5. And if I plot it there, so it means this value is plotted here. So it means the same values in the depth for these two logs are represented by this dot here. And similarly, all these values in this log at different depths are represented by all these various samples. And if I go in the reverse direction, if I just create a polygon or circle, so it means this point is there. So it means this data sample in the depth domain would be represented by this thing. So it means what is happening, that if I select anything from here, the same thing in the depth domain would be plotted here. And if I select anything here, or if I take the samples here, they would be plotted on the cross plot. So they are interrelated. So in this way, when we make various polygons within the cross plot, so it means their corresponding samples in the depth domain are then highlighted according to the corresponding values. So this is what we are doing mostly in the Facies modeling. So here you can see it's the same data, and here I have made one polygon like this. So it means all the samples which have been trapped within this polygon in the depth domain, they have been colored in yellow, and similarly in rest of the colors, all the samples that have been within those polygons, they have been colored accordingly. So it means basically this is depth domain, and this is the cross plot is the attribute domain. So in this way, basically we try to interpret the data. Like in this case, we are differentiating sand and shale, or in between sandy shale. This is basically the Facies modeling that we are doing. So this cross plots using these polygons is one way of interpreting the. So basically this cross plot, and when we have made these polygons within this, so we would call this as a rock physics template for that area. So suppose I have the acoustic impedance from seismic, and I have computed the VP/Vs ratio from the seismic. So I have two cubes of seismic. One is the acoustic impedance, and the other is a VPVS. In this case, this is 1D data. So the seismic cube would be a 3D data. And if I plot that data onto this template and apply this template to this, so it means as a result, in 3 dimensions, I would get a cube where all these colors would be, and so it would be highlighting sand and shale bodies. So this would be one way of interpreting the data. So it means these rock physics templates, we develop them using the petrophysical logs, but now from the seismic data, using inversion and then rock physics equations, we compute the cubes from the seismic for such parameters, and then we plot these cubes onto a rock physics cross plot and apply the template, and so we get the interpretation. This is how the things are being done. This is another example. You must have seen all these types of curves. So it means people have worked on different cross plots and identified various things, that if the data lies within this part, so it would be sandstone, like in this case, it can be limestone and so on. So it means using these cross plots, the data is clustered there. We can differentiate it into various facies. So on the basis of these templates, we are able to interpret the data. In addition to the making these polygons within the data, we can also cluster the data. That is a mathematical technique mostly used, and later we would see that if we increase the dimension of this cross plot, so it means we would not be able to make the polygons. So the new modern techniques are the clustering techniques, such as the k-mean clustering technique. So instead of making the polygons, we just define, like in this case, we have defined 3 classes of the data. So based on their localization of the data and the concentration of the points, the algorithm has clustered the data into 3 different facies. So this is another way of classifying the data, and this is a more modern concept of doing the same things. And if we increase the dimensions, that would be more useful. And all these techniques, like this clustering, are more commonly used in machine learning algorithms, which are also applied for interpretation of all these rock physics parameters. Okay, one thing now, if we conclude here, and now I have an empirical relation which computes Poisson ratio from acoustic impedance. So it means what would happen? I can, using this empirical relation, which has been derived from the well logs, I would apply this equation to seismic inverted cube, and I would get another cube of Poisson's ratio. And so on, I can generate various cubes using different empirical relations. So when I use the regressions, I am computing one property from another. Whereas in case of the templates, actually, what is happening? I'm clustering the data into different facies. And when I apply it, the result is not any physical property, but it is something to various facies. So it means the difference between the two that we need to understand is that in empirical relations, we derive equations through which we convert one set of property into the other property. But that is a Poisson ratio. So now looking at the Poisson ratio, that further needs to be interpreted. Whereas using these templates or cross plots, once we have two properties, so it means we can cross plot them, and using the template, we can then classify the data into, suppose, sand and shale. So basically, practically we use both of them. Suppose I am using the empirical relations, computing various cubes using the empirical relations, and now using those cubes, I input them into this template, and then I classify them into a more geologic type of interpretation, that is identification of the lithologies. Okay, finally, this attribute space. I just mentioned about the cross plots that we have seen. So here we can see that we have a cross plot between p-wave velocity and shear velocity. So this cross plot is basically a two-dimensional attribute space. Similarly, we can have a cross plot of density and p-wave. And similarly, we can have a cross plot of shear velocity and density. So here we can see 3 different cross plots. And if these are 3 different rock physics templates, so using them, we can interpret the data and we can get the results. And naturally, the interpretation would match to a certain degree, but there could also be certain variations. So all these cross plots are basically attribute spaces of 2 dimensions. So when I name them attribute space, because we can increase the dimension of this attribute space, and I can make a 3-dimensional space. And now if I plot them like this, So it means on one axis we have Vp, on other axis we have Vs, and on the third dimension axis we have this density. And if I plot the data, it would be plotted in this 3D cube. So this Vp, Vs, this plane represents this cross plot. Then this plane basically represents this cross plot, and this cross plot is represented by this plane. So all these three individual two-dimensional attribute spaces or cross plots are together represented by this three-dimensional attribute space. So now, like in the previous case, we were making the polygons like that to differentiate the things. We cannot do it in the three-dimensional space. So here, the clustering techniques would be more useful, because the clustering techniques compute the distances between the sample points and then cluster them into the central nucleus. So all those k-mean clustering and these algorithms are more useful, and that is the future of rock physics, that we would be having more higher order dimensional attribute spaces that would be more useful in interpreting the data. Okay, that was all about the basic concepts that we have revised. A session on the Wavelet software, but before that I would like to introduce a little bit about the Wavelet software. Wavelet software is basically free educational software, and it just needs a license to be obtained, and then you can use it. It has a perpetual license, which means once you get the license, you can use it on multiple machines, and it would be valid for all the future versions of the software. Originally, the software has a computer-based training tools. Predefined training sessions are available in it. These are not PowerPoint type slides, but using signal processing algorithms, like understanding the signal processing concepts behind seismic. So in this computer-based training sessions, a student can go through and they can learn different things. Then the second part is experimentations. Here the user has different experimentation dialogues. They can input the parameters and they would get the results. So if the student has certain questions in mind, they can put those parameters and they would see the results. I would give an example, like in processing, we don't have velocity reversals generally, because we are talking about RMS velocities, but in the real, geologically, we can have a low velocity layer. So if we just put the velocities there and we can identify what would be the situation geologically when in the seismic RMS velocities we are going to get the reversals. So we can adjust the values and we can get the answers in that. And in addition to that, the wavelets is also used for processing and analysis at the educational level. So like it has a lot of tools for reading the petrophysical logs, edit them, and then finally use all these rock physics regressions and Facies modeling type things on it. And it is, since it is just an educational software, so everything is quick. You don't need to make any project for that. Just load the LAS file and you can do most of the things. Development platform. So it has its programming libraries which are available to software developers, so they are able to develop new things or add new functionality into the software. So this was just a brief about the wavelets. So what we would be covering in the coming session now, an introduction to the wavelets, that is practical introduction, a little view about the computer-based training modules, a quick review of the experimentations, and then loading of the logs, their QC and editing, and all the basic conventional petrophysics things. That would be a just quick view of that. And then we would focus more into regression analysis and finally into Facies modeling. So that would be next thing that we would be doing. And that Facies modeling we would be using through this geometric polygons as well as key main clustering. Thank you.